Hello everyone, and welcome to this video, continuing sections 6.3/6.4, and particularly on the objective functions expressed as Taylor series. So in this video, I'm going to be going over a part of a preview version of a Newton Alta assignment for this section 6.3/6.4. But I'm only going through the problems under the objective heading called Functions Expressed as Taylor Series. Now please understand that the questions I see in this video may not be the same questions that you see when you work on the assignment yourself. But my hope is that these questions are similar enough, and watching me work on them here will help you in some way when you go to work on the assignment yourself. All right, so here is the look of our Newton Alta assignment page. In the upper left-hand corner, you have the title of the section, the title of the assignment. You won't see the word preview. In the upper right-hand corner, you have your mastery bar that tells you how far along you've gotten in the assignment. Now, again, I will not be completing the entire assignment here. Because next to this, you can see the activity log that shows you each individual objective. Now, I've already made videos for the Taylor and Maclaurin series heading, the Taylor's theorem with remainder heading, and the binomial series heading. So again, this is on functions expressed as Taylor series, the final objective. And the only sub-objective here is find the Taylor expansion of common functions. And of course, it could be Taylor or Maclaurin. Or Maclaurin series are just Taylor series centered at 0. All right, then on your main page, current objective. Below that, a question related to that objective. And then at the bottom of every question, there should be a feedback button. So if you're seeing any issues with the question or the answer explanations or anything, you can send feedback directly to Newton. And hopefully someone from their support staff can get back to you quickly and help you with your issue. You will not see this instructor cheat button. This is for instructors only. But you should see a more instruction button. So if you're ever struggling with a topic or a particular question, you can click on more instruction and it'll take you to a page with further reading to do or videos to watch or both. And then it'll give you questions related to that instruction that you can work on while the instruction is still available, and you can keep referring back to it. And you can keep using this more instruction whenever it's available to get through the entire assignment if you wish. Okay. So like I said, the only objective we're really working on here is find the Taylor expansion of common functions. All right. And we're asked here to find the first 4 non-zero terms of the Maclaurin series for the function below. Now this is f of x equals 9 times, now this SINH function, this is the hyperbolic sine function of 4x cubed. So I'll explain briefly what the hyperbolic sine function, and there's also a hyperbolic cosine, sometimes referred to as sinh and cosh. I'll explain to you briefly what those are, and they're asking for, right, the Maclaurin series, or at least the first 4 terms, non-zero terms of the Maclaurin series. All right, so we'll talk about some Maclaurin series for some common functions. So first off, a very brief introduction to what are called the hyperbolic trigonometric functions. I'll just say hyperbolic trig. So you have the hyperbolic sine. So it's sin, just like sine, but then you have a little h after the sin. Hyperbolic sine of x. And this is defined to be, these are defined using exponential functions. So you may have come across these before, but I've also seen in courses at certain places where if exponential functions are taught extensively, these aren't even brought up. All right, so you may not have seen these before, even though you're in Calculus 2. But the way the hyperbolic sine is defined, the hyperbolic sine of x is half of e to the x, right? That's base e, an exponential, minus half of e to the negative x power. All right. You can also write this as e to the x minus e to the negative x, all divided by 2, right? Because this would be all over 2. But I'm going to look at it this way, the way I know here. And then hyperbolic cosine, C-O-S-H, right? It's like cosine with an H after it for hyperbolic. The hyperbolic cosine of H is defined again using exponential functions, and it's very similar to the hyperbolic sine. You have half e to the x plus half of e to the negative x, or e to the x plus e to the negative x divided by 2. And then, of course, you have hyperbolic tangent, right? So it's tan with an h after it, like tangent, but with an h for hyperbolic. And this is your hyperbolic sine divided by hyperbolic cosine, just like for trig, regular trig, circular trig functions. Which, if I, divided these, the 2's would cancel, and you'd have e to the x minus e to the negative x in the numerator, divided by e to the x plus e to the negative x in the denominator. And then the reciprocals of these would be, corresponding to the reciprocals when you were working with regular trig functions, right? Sine, cosine, tangent, the circular trig functions. So the reciprocal of hyperbolic sine would be called hyperbolic cosecant, CSCH. The reciprocal of hyperbolic cosine would be hyperbolic secant, SECH. And the reciprocal of hyperbolic tangent would be hyperbolic cotangent, COTH. And it would just, flip all of these fractions here. All right, but we're going to mostly focus on these two, if any of them today. And the first problem I'm seeing here is involving this hyperbolic sine. Right? Now we're asked to write the Maclaurin series. We're asked to write the Maclaurin series in this first problem. So remember that's just centered at 0 for a function involving hyperbolic sine. Well, I'm going to do just hyperbolic sine for right now. And just use the fact that hyperbolic sine is, again, defined this way. It's half e to the x minus half e to the negative x. And we've seen, all right, if you go back to the video from this section on Taylor and Maclaurin series, we have seen that e to the x, right, the Maclaurin series for e to the x was this, the sum from n equals 0 to infinity of, and then, the derivative of this, every derivative of this is e to the x. So the value of every derivative at 0 was 1. So we have 1 over n factorial times x to the nth. So it was x to the nth, pardon me, over n factorial. So going through here, oh, and this, the interval of convergence was all real numbers, right? This series converged to e to the x for any value of x. So that's going to be the case for our hyperbolic sine and also hyperbolic cosine functions. So if I go through and use this fact, all right, this hyperbolic sine of x, just x, would be half of this series, right? Half of e to the x. So the sum from n equals 0 to infinity of x to the nth over n factorial, then minus half, and then the series for e to the negative x is the same as for e to the x, but I'm replacing x with negative x. So we got the sum from n equals 0 to infinity of, negative x to the nth over n factorial. Now I can factor the half out, and since both of these, start at n equals 0, we can put these together. So this will be half of the sine n equals 0 to infinity of, x to the nth over n factorial minus the sine from n equals 0. Again, we're going to put these together in a second. Now, negative x to the nth is the same as, negative 1 to the nth times x to the nth. And, both of these series converge for any value of x. So for any value of x, these can go together, and they're starting at the same value here. The same value of n is 0. So this is half of the sum equals 0 to infinity. And they're both something over n factorial. I can factor out the x to the nth. And then the numerator be 1 minus, negative 1 to the nth. And, here is a perfectly valid Maclaurin series for hyperbolic sine of x. Now, though, look at what happens, though, when I write out the first several terms of this. And I'm going to put the half in after, but this will be half of the quantity. Now, when n equals 0, you'd have 1 minus, and then negative 1 to the 0, negative 1 to an even power would be 1. So 1 minus 1 is 0, so you get 0 for the first term. And then when n equals 1, negative 1 to the first is negative 1. 1 minus negative 1 is, negative 2, or is it 2, just positive 2, sorry. 1 minus negative 1 is positive 2. So plus 2 over 1 factorial times, x to the first. And then plus, and then when and again, all the even powered terms will be nothing, because negative 1, when n equals 2, this will be 0 up here again. So 0x squared, then plus, and then again, when n equals 3, when n is odd, this is going to be 2. And then 2 over, 3 factorial times x cubed, and so on. So all that's going to really remain are the odd powered terms, and if I multiply every single one of them by a half, all these 2's become 1. So when I do this, I'll have 1x, right? 1x plus 1 over 3 factorial x cubed. And then you can hopefully see that eventually the next term would be 1 over 5 factorial x to the 5th, and so on. So instead of leaving, now this sum is perfectly valid. This right here that I have in the box, this is a perfectly valid Maclaurin series for the hyperbolic sine of x. But it includes a lot of terms that are just 0. So if we look at this here, we got we have terms that only really involve odd numbers. So I'm going to write this as a sum from n equals 0 to infinity of, I have x to an odd power starting with 1. Now remember, odd powers are usually expressed as a multiple of 2 plus or minus 1. Now I want when n equals 0 to get positive 1 up here, so I'm going to have that be x to the 2n plus 1, and then this is divided by that same odd number factorial, 2n plus 1 factorial. Right? Writing it this way takes care of all the terms, right? Every single term is accounted for, and it gets rid of all the 0 terms if you write it this way with the odds 2n plus 1. So there's and again, this should converge for all real x, okay? You can double check by using the ratio test and whatnot. But this should converge to this, hyperbolic sine of x for all real x. So if this is our series, all right, so again, I'll write this up. Hyperbolic sine has this Maclaurin series, the sum from n equals 0 to infinity of, odd powers of x divided by that same odd number factorial. And then, of course, the interval of convergence, this will be convergent, this series for all real numbers. Now, I'm not going to do this for all the functions we see. What I'm going to do instead is refer you to section 6.4 of the openstacks.org, right? This is openstacks.org, their Calculus Volume 2 text. Go to section 6.4 called Working with Taylor Series, and eventually, scroll down enough, you'll see common function, a little table here, where they have common functions and their Maclaurin series, right? The power series representing them at x equals 0, and then also where those series, for what values they will converge. And eventually down here, well, they don't look like they have hyperbolic sine or hyperbolic cosine, but I just wanted to point out that, for e to the x, I wrote that one up earlier. Here's for sine of x. Now sine of x, regular sine of x, it's pretty much like the hyperbolic one, odd powers of x over odd factorials, but alternating. See this -1 to the nth power in front? And then cosine of x has even powers of x over the even factorial, but alternating, right? You got this -1 here, and those all converge for all real numbers. We had our 1 over 1 minus x, the geometric series that we've seen plenty that converges from -1 to 1. And then a Maclaurin series for the natural log of 1 plus x, inverse tangent of x, and the binomial series, right? We saw a video, the video right before I released before this one is on the binomial series, this 1 plus x to the r expressed as a series. So yeah, so refer to this table, and I'm going to keep referring to these as we go through the video here. Now we do have this. Now in our question, right, the function we were given was 9 times the hyperbolic sine So again, sometimes referred to as the sinh or sinh. I've heard sinh mostly. Of 4x cubed. So all I'm going to do is take the one we know for hyperbolic sine of x and replace x with 4x cubed. All right, replace x with this 4x cubed. And of course, we got the times 9 in front. Right? So this will be 9 times, and then this hyperbolic sine of 4x cubed should have this Maclaurin series, the sum from n equals 0 to infinity of, and then instead of, x to the 2n plus 1, it'll be 4x cubed to the 2n plus 1 divided by, and then 2n plus 1, factorial. And then all I'm going to do, now you can expand on this or whatever, but they just want the first 4 non-zero terms. So this will be 9 times, and we'll distribute the 9 after I get the first 4 terms here. Now when n equals 0, this will be 4x cubed to the first power divided by 1 factorial plus, and then when n equals 1, it'll be 4x cubed to the third power divided by 3 factorial plus, when n equals 2, 4x cubed to the fifth over 5 factorial. And then finally, the fourth non-zero term, right? The fourth term of this Maclaurin series, 4x cubed to the seventh over 7 factorial. And then, of course, there's more to it, but we're only looking for the first one. And then I'm going to distribute the 9, of course, right, to all 4 of these. So the first one is going to be 9 times 4 x cubed. That's 36, x cubed. And then we have, 4 cubed. 4 cubed is 64. Yeah, I'm going to go to that. So 9 times, 64 over 6, right? 3 factorial is 6 times x to the 9th power, x cubed cubed, plus 9 times 4 to the 5th over 120, right? 5 fact. I might just type it in like this and see if they take it. And then times x to the 15th power. And then finally plus, 9 times 4 to the 7th over 7 factorial, which is, I believe, 5040. No, wait, this would be 6 factorial would be 7. Yeah, 5040. But then times x to the 21st. So I'm actually going to see what happens when I type in stuff like this. All right, just the first 4 non-zero terms of this series. So f of x equals, now first one was no problem, right? It was 36x to the third plus, and then 9 times 4 to the third divided by 3 factorial times x to the 9th plus 9 times 4 to the 5th divided by 5 factorial times x to the 15th plus, and then 9 times 4 to the 7th divided by 7 factorial times x to the 21st. And that's all they're asking us to do. Let's see if it takes it the way I've typed it. Yes. Now you see they actually multiplied things out and simplified fractions. But yeah. Okay, and again, after you submit an answer, You'll be given some sort of answer explanation. Please look through these. If you got it right, just glance through it just to make sure you got it right for the right reasons, or make sure that there's no errors in the answer explanations. Who knows, maybe they'll do something in a way that you like better and might want to try for future problems in that objective. Now, of course, if you got it wrong, definitely look through the answer explanations, trying to figure out why you were wrong, right? If you can see that, that's half the learning, learning from your mistakes. All right, next question here. So here they're asking us to find the radius of convergence of the Maclaurin series again for the function below. All right, now this is an inverse tangent of something. And like I said earlier, I'm going to keep referring to this table if we see our common functions. So here's the Maclaurin series for the inverse tangent of x, and I'll write this out. And we also have when it converges, this series. So I will write this. You can figure it out by doing derivatives and plugging in 0, right? Again, I'm just referring to that table to speed things up. So we have the inverse tangent of x. Actually, I shouldn't use f because that's in the problem. But inverse tangent of x, just plain old x, has this series that converges to it. The sum from n equals 0 to infinity of -1 to the nth, so it's alternating, multiplied by odd powers of x. See, it's x to the 2n plus 1, like in the hyperbolic sine function, but then divided by just that odd number. Not the odd number factorial, just the odd number. And this series will only converge to this value, this inverse tangent of x, if x is between -1 and 1, but also including -1 and 1. Those are part of this interval of convergence. All right, now the function we're given is the following. F of x equals, the inverse tangent of, and then, something I'm going to replace x with. We have the 5th root of x divided by 5. Well, this should be equal to, the sum from n equals 0 to infinity of, -1 to the n, and then I'm replacing x with this 5th root of x, 5th root of x divided by 5, to the 2n plus 1 power to some odd number, divided by that odd number. But only when this value replacing x here is between -1 and 1 inclusive. So only when the 5th root of x divided by 5 is less than or equal to 1, and at the same time greater than or equal to -1. And then I multiply by 5 here. So the 5th root of x would have to be between -5 and +5. And then take raise everything to the 5th power to undo that 5th root there. Now 5 to the 5th is 3,125. So the absolute value of x here has to be less than or equal to 3,125, right? The center's at 0, right? And the distance to either end here is 3,125. That's called the radius of convergence, remember? R, the distance from the center to either end of the interval of convergence. And this is what they're asking me for, right? The radius of convergence for this series. So yeah, this would converge over the interval negative 3,125 to positive 3,125. So again, with the center being 0, this radius of convergence is 3,125. I've not actually run it on. I just used what we knew the Maclaurin series for inverse tangent was. They performed the whole ratio test thing here. But either way, we get the same result. Here again, Maclaurin series once again. Now notice this is just e to the something. I've got 2 times a power an exponential, e to some power, e to the 4x cubed power. So I've already written up the Maclaurin series for e to the x back in the first problem. I'll do it again here, and it's also in that table I've been referring to, that table from section 6.4 of the OpenStax text. So remember, e to the x should be equal to the following infinite series. Sum from n equals 0 to infinity of x to the nth divided by n factorial. And this is for any value of x. This series will converge no matter what x is. Now the function we're given is, 2 times e to the 4x cubed power. So this 4x cubed power is going to replace x, right? It's not just e to the x, it's e to this, 4x cubed. And that's all I'm doing. So when I write this as a power series representation, right, this would be 2 times, and then the sum from n equals 0 to infinity of, and then instead of x to the nth, I'll have, 4x cubed to the nth, and then divided by n factorial. And again, this is all getting multiplied by 2, and no matter what x is, this should work, right? So this is for any value of x. Our series will converge to this function value. Now, just like an earlier problem, they're only asking for the first 4 non-zero terms of the Maclaurin series. So this is 2 times, and then when n equals 0, I'd have 1 over 1, right? So just 1, plus, when n equals 1, we'd have 4x cubed, to the first, divided by 1 factorial, which is just 1, so this is 4x cubed, plus, and then we have 4x cubed squared, right, divided by 2 factorial, plus, and then 4x cubed to the third power divided by 3 factorial, and that's for non-zero terms. So I'm going to go plus dot dot dot, and then we'll distribute the 2 to all these, and here we go. 2 times 1 is 2, plus 2 times 4x cubed would be 8x cubed. Then 2 and the 2 here would cancel. I'd be left with 16x to the 6th, 4 squared, times x to the third squared. And then 2 times this, 2 over 3 factorial is 6. So that'd be 2 over 6, that's 1/3. Then 4 cubed is 64, so plus 64 thirds x to the 9th, right? And then so on. But this is all they want, right? The first 4 non-zero terms of the Maclaurin series for this function. So back here, right, f of x equals 2 plus 8x to the third plus 16x to the 6th plus 64 thirds x to the 9th. And that's it. Great. All right. Once again, the first four non-zero terms of some Maclaurin series, and it involves e to a power again. So this is very, very similar to the last problem. So I'm just going to cover up the work from the last problem here, and all we're changing, right, here's the Maclaurin series for e to the x. But this time, the function we're given is 3 times e to the 4x to the fifth power. So now this 4x to the fifth power will replace x in the Maclaurin series for e to the x. All right, so this will be 3 times the sum from n equals 0 to infinity of, and then instead of x to the nth, right, we'd have this 4x to the fifth to the nth divided by n factorial. And again, all they want is the first four non-zero terms. So we got 3 times, and we'll distribute the 3 in a minute. Now when n equals 0, this would be 1, plus, and then when n equals 1, this will just be 4x to the fifth, plus, when n equals 2, you got 4x to the fifth squared over 2 factorial, plus when n equals 3, you got 4x to the fifth to the third, divided by 3 factorial, and so on. Right, and we'll distribute the 3. Right. So first term, 3, plus second term, 12x to the fifth, plus now third term, 4 squared is 16, times 3 is 40. Well, 16 over 2 is 8, times 3 is 24, so plus 24, x to the 10th. Right, it's x to the fifth squared. Then finally, 3 divided by 3 factorial would just be 1/2, right? 3 over 6. And then 4 to the third is 64, divided by 2 would be 32. And then x to the 15th, and so on. And there's what they want though, right? Just the first four non-zero terms. So f of x equals 3 plus 12 x to the fifth plus 24 x to the 10th plus 32 x to the 15th power, and so on. Wonderful. So yeah, very similar couple problems there. All right, now this one's like a few problems ago, right? Find just the radius of convergence of the Maclaurin series for the function below. Now this is another one of those familiar functions, common functions, the natural log of 1 plus something, which I'll go back to that table from the section 6.4. You see this line right here. The natural log of 1 plus x has this series converging to it, but only for values of x between -1 and 1, including 1 but not including -1. And it's the sum from n equals 1 to infinity of -1 to the n plus 1. So some alternating series, right, times x to the nth power divided by n, right? Just n, not n factorial. So I'll write this up, and then we'll look at the function we're given and make a little substitution. So we're seeing that the Maclaurin series for the natural log of 1 plus x is the sum from n equals 1 to infinity of -1 to the n plus 1 power times x to the nth over n. And this is in this interval, though, between -1 and 1, including 1, but not including -1. Now the function we're given right, is the natural log of 1 plus, not x, but 3x. So I'm just going to be replacing x with 3x, right? X is replaced by 3x. I'm just replacing x with 3x in this series. And then also over here for this interval, the only way it's going to happen, the only way this function has a series converging to it, is if this 3x, whatever this is between -1 and 1. So this should be equal to the sum, and equals 1 to infinity of -1 to the n plus 1 power times, x is replaced by 3x to the n over n. But this is only convergent if 3x is, between -1 and 1, including 1. And then I divide everything by 3 here, and we say that x would then have to be between -1/3 and 1/3. Now, if the center is at 0, right, this is a Maclaurin series, the middle of this interval is at 0, and the distance to either end is 1/3, right? So the radius of convergence here is what they're asking for, is 1/3, right? The distance from the center to either end of the interval of convergence. So the radius r of convergence for this series, 1/3. Now again, they did the ratio testing, but yeah, same result. All right, here we go. This one's incredibly similar. You see how the function we're given is the natural log of 1 plus something. So just like this here. All right, so I'm going to, again, just kind of like before, cover up this work. Here's the Maclaurin series for the natural log of 1 plus x, but we're going to replace x with 5x to the fourth. Pardon me, right? Our function here was, natural log of 1 plus 5x to the fourth. So this 5x to the fourth, right? This will be replacing x in the series and in this, interval of convergence. So it'll equal the sum, again, all they want is the interval of convergence. So the sum of something, if, 5x to the fourth is between -1 and 1. Now, if you try to solve for x here, that means x would have to be between the negative fourth root of 1/5 and the positive fourth root of 1/5. All right, dividing by 5, doing fourth roots. Now again, if the center in between these is 0, and the distance from 0 to either end is this fourth root of 1/5, right? So here's what I'm going to be typing. Now I'm going to actually type 1/5 to the 1/4 power, right? Because I don't want to look for the fourth root symbol. Although it's right here. Never mind. It's right here. So the fourth root of 1/5 is the radius of convergence for the series that converges to this function. Now they wrote it a different way, but I had something equivalent, right? So they took it. All right, so this time, so this will be, okay. They're asking us to find the first 3 non-zero terms of the Maclaurin series for the function below by first writing its antiderivative as a series and then differentiating. That's really unnecessary here. I'll show you both ways, but all right, so watch. All right. So I'll show you the way they're asking. So here's our function. All right, f of x equals 2x times e to the x squared power. Now what they're asking us to do first is do the integral. All right, the integral of this function with respect to x. Now this should just be e to the x squared plus some constant, right? Remember the Maclaurin series for e to the something, right? You know what? I'll do it this way. The Maclaurin series for e to something, right? Little box is the sum from n equals 0 to infinity of whatever's in that box to the nth power divided by n factorial. And it's for any value you want. All right, it's this series will converge no matter what value is in there, right? For all real numbers. So then this e to the x squared plus some constant should be equal to the sum from n equals 0 to infinity of x squared. All right, so you see how x squared is the thing in the box here. So x squared to the n. Now that would be x to the 2n, right? X squared to the n, and divided by n factorial. And if you look at the first several terms of this, right, when n equals 0, you'd have 1 plus when n equals 1, you'd have x squared over 1, and so on. And then you can find the value of this constant here, right? If x equals 0, then e to the 0, you'd have 1 plus c on the left equals, and then 1 plus a bunch of zeros on the right, implying the value of this constant is 0. So I don't really need the plus c, because it's 0. Right. So what we're seeing here is that the integral of this function we're given has the following series. Sum from n equals 0 to infinity of x squared to the n, right, x to the 2n, divided by n factorial, which if I'll write out the first 4 terms of this, and you'll see why. Because they want the first 3 non-zero terms of the series for our function here. Now this function is the derivative of this, right? This is the integral of our function. So if we want our function back, we got to do the derivative. So if I write out the first 4 terms of this, it'd be 1 plus x squared plus x, 1, when n equals 1, you have x squared over 1. When n equals 2, you got x to the 4th over 2. When n equals 3, you got 1 over 6, 1 over 3 factorial times x to the 6th, and so on, right? And then you differentiate, right? Right? Well, the derivative of this integral will be our function, right, which is this 2x times e to the x squared. And if I differentiate this term by term, the first non-zero term will be 2x, because the first term's a constant, the derivative will be 0. So 2x plus, and then 2x, half of 4x cubed, so 2x cubed, plus, and then 1/6 of 6x to the 5th, so just x to the 5th. And there you go. All right, here's what they want, the first 3 non-zero terms of our series. Now that's great and everything, but like I said, I don't think any of this is necessary. So watch this, okay. Remember, we got the Maclaurin series for e to something. So this is going to be 2x times, and then I'll write the Maclaurin series for e to the x squared, right? Just replace the thing in the box with x squared. So that's the sum from n equals 0 to infinity of, x to the 2n, x squared to the nth over n factorial. And then I multiply it all by 2x. So that's the sum from n equals 0 to infinity. And then when I multiply by 2x, I got 2 in here, sure. And then x times x to the 2n would be x to the 2n plus 1 divided by n factorial. And let's write out the first, 3 terms of this. When n equals 0, you got 2 times x to the 1 over 0 factorial, so 2x. Plus, when n equals 1, be 2x to the third over 1 factorial, so 2x to the third. When n equals 2, you'd have 2 times x to the fifth over 2. So plus x to the fifth, and so on. And you see how that's exactly the same as what I got earlier with doing what they told me to do? Integrate, then write as a series, then differentiate. Kind of silly if you ask me to do all that for this problem. There may be other functions that'll be useful for, but because this was just some polynomial times an exponential, and I know how to write a series for the exponential, you could just multiply that series by the polynomial and be done with it. Yeah, so the first 3 non-zero terms are 2x, 2x cubed, and x to the fifth. 2x plus 2x cubed plus x to the fifth. Right. So this one, again, I don't really see why integrating first and then differentiating will help. I will show you. All right, I'm going to use a series we already know and then just multiply it by some polynomial. And we'll get the first 3 non-zero terms of the Maclaurin series for this function. So I'm going to tell you right now, the series I'm using here will be the binomial series. That's the last line in this table here from section 6.4 of your OpenStax book. And again, if you don't recall what this notation, this R over N thing in the parentheses meant, all right, I'll write it up here real quickly again, but I did a whole nother video on the binomial series before this, if you want to check that out. All right, so I'm going to write this up, and we're going to use it to help us with this series here. A series for this function. So again, recall that, 1 plus something, again, I'll just use x, or you could put a box here, to a real number power, right? R is just some real number. You could write this as a series. Sum from n equals 0 to infinity of this, big parentheses, and then they say R choose n, R on n, but that usually implies division. This isn't division. Notice there's no fraction bar here. And then times, x to the nth. There's the Maclaurin series for this. But this is only convergent, though, for values of x between -1 and 1, though, right? This series only converges to this function for values of x between -1 and 1. And this R choose n, and just to refresh your memory from the last video, this is R times R minus 1 times all the way down to R minus and then 1 less than n. So R minus the quantity n minus 1, or if you distribute the negative, R minus n plus 1. All that in the numerator. And then n factorial, right? N is going to be a whole number here, 0, 1, 2, 3, 4, whatever. R can be any real number. N is some whole number. And you got n factorial in the denominator. So that was the Maclaurin series. This is the Maclaurin series for a binomial to a power, right? Called the binomial series. Right, sorry about the. All right, so I'm going to use this for our function. Function we're given, you have negative 16x cubed divided by 3 times the quantity 4x to the 4th plus 1 to the 4/3 power. Now they told you to integrate this thing, which you could. It wouldn't be hard to do with a u substitution or whatever, but here's how I'm seeing it. You have negative 16/3 x cubed, right? Negative 16x cubed over 3 times, and then this is 1 plus something, right? That's going to replace the x here. 1 plus 4x to the 4th to the negative 4/3 power. So I have something I can write as a series right now, and then we're going to multiply by this polynomial, this negative 16/3 x to the 3rd out here. So this 4x to the 4th is replacing x in this series. And the value of r is negative 4/3. So this should be negative 16/3 times x cubed times the following series. All right, sum from n equals 0 to infinity of, this negative 4/3, choose n, times, and then instead of x to the nth, this 4x to the 4th to the nth. And again, all they want is the first 3 non-zero terms. So what I'm going to do is keep this negative 16/3 x cubed out here for right now. And then I'm just going to put out the first 3 non-zero terms of this series, and then we'll distribute the negative 16/3 x cubed. Now remember, negative 4/3 choose 0 times something to the 0, that's all 1. Plus, then negative 4/3 choose 1, which will just be negative 4/3 times, 4x to the 4th to the 1st. Then plus negative 4/3 choose 2 times 4x to the 4th squared, and then you'd have a bunch of other terms after that. Now I'll write out what these are, and then we'll distribute the negative 16/3 x cubed. So negative 16/3 x cubed times, you got 1, minus, now 4/3 choose 1, negative 4/3 choose 1 is negative 4/3, but then times 4 would be negative 16/3, x to the 4th. And then this, right, this negative 4/3 choose 2, that would be, negative 4/3 times 1 less, so negative 7/3, right, negative 4/3 minus 1, divided by 2 factorial, which is positive 14/9, right? So this would be 28/9 cut in half, 14/9. And then this gets multiplied by 4 squared, right? And 14 times 16, 14/9 times 16. 14 times 16 is 224. So plus 224/9 x to the 8, right? Because it's 4 x to the 4th squared here, and so on. And then we distribute this negative 16x to the 3rd, negative 16/3 x cubed. All right, so I'm going to do this. You have negative 16/3 x cubed times 1, and then plus 16 thirds squared, really, right? Because 16 thirds times 16 thirds, x to the 7th, right? X cubed times x to the 4th, and then minus, I could multiply this out, but you know what? I'm going to do this. 16 times 224 over 27 and type it in this way. And I know we have a calculator. I can go to a calculator and do this, but x to the 11th, and there we go. So that all they want are these first three non-zero terms, and I didn't need to integrate and differentiate and all that. Right, and maybe I will actually go to a calculator here to get these values, but we have negative 16 thirds x cubed for the first term plus now 16, I could do this one. 16 squared is 256. And then 3 squared is 9. So the next term is 16 thirds squared, 256 over 9, x to the 7th. And then why not? Let's go to Desmos here. Sorry, I didn't have it readily available. Saw some news there from the day, so you might be able to figure out what day I'm doing this. 16 times 224, 3,584. Divided by 27, this might actually reduce, say, reduce this to, it's just 3,584 over 27. So then minus 3,584 over 27, x to the 11th. And then dot, 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 right? Plus dot, dot, dot. Yeah, again, they differentiated and then integrated, then differentiated. I just saw a series that I could, I could write this as a polynomial times some series I already know. All right. All right, so here we have find the radius of convergence again for another Maclaurin series. Now this one's like the geometric 1 over 1 minus something. You've seen this plenty if you've been watching my, chapter 6 videos. But I will, again, number 1 over 1 minus something, 1 minus x. There's a series that converges to this, and that's just that geometric series, the sum from n equals 0 to infinity of just x to the nth. But this series only converges to this if, this x is between -1 and 1. Well, the function we're given is 1 over, 1 minus x squared, which, this x squared will replace the x's up here. So this will be the sum from n equals 0 to infinity of x squared to the n, or x to the 2n. But this will only converge if x squared is between -1 and 1. But that's going to only be happening if x is between -1 and 1. So the radius of convergence is still 1. Right, centered at 0, and the distance to either end of this is 1 unit. So still a radius of convergence of 1 unit. Again, they do the ratio test stuff, but wow, they actually did the binomial series here. I don't think that was the best choice, but okay. And here we go. First 4, we've seen problems like this also. All right, first 4 non-zero terms of the Maclaurin series for this function. And it was the natural log of 1 plus something. All right, and again, we've seen this natural log of 1 plus something, the Maclaurin series for that here, when it converges, but they just want the first 4 non-zero terms of that series again. All right, so Again, I'll write out the Maclaurin for that common function. Right, the natural log of 1 plus something plus x can be written as the sum from n equals 1 to infinity. Right, it was 1 to infinity of, and then it was alternating. You had this negative 1 to the n plus 1 power times x to the nth over n. Right, no factorials. And this was only convergent for values of x between negative 1 and 1, including 1, but not including negative 1. Now our function, right, the function we're given is the natural log of 1 plus 2x squared. So again, this 2x squared is going to replace all the x's up here. All right, so this should be the sum from n equals 1 to infinity of, negative 1 to the n plus 1 times, and then instead of x to the nth, I have this 2x squared to the nth, divided by n. And I'll just start writing it. All right, now I know I could write the interval of convergence and whatnot, but they just want the first 4 non-zero terms once again. Okay, so when n equals 1, this would be negative 1 squared, so positive, and then 2x squared to the first over 1. So that's 2x squared for the first term. Plus, when n equals 2, we'd have a minus, right, or negative 1 to the third power times 2x squared over 2. Then plus, when n equals 3, 2x squared cubed over 3. And then minus, when n equals 4, 2x squared to the fourth over 4, and then plus blah, blah, blah. And honestly, I think you can just type this. But I'll simplify things. This would be 2x squared. Now this would be 4x to the fourth over 2, so minus 2x to the fourth. This would be 8/3 x to the sixth. And then 16 over 4 is 4, so minus 4x to the 8th, and so on. But again, all they want here is the first 4 non-zero terms of this series. So 2x squared minus 2x to the fourth plus 8/3 x to the sixth minus 4x to the 8th. Right, that could be good. Wonderful. Another radius of convergence problem. So again, we have an inverse tangent of something. And here's your Maclaurin series for inverse tangent of x. And this series converged when x was between negative 1 and 1, including negative 1 and 1. So then the radius of convergence was 1. So I'm just going to jump to the right column here for the radius of convergence, or we'll look for the interval of convergence first. So here's our function. All right, let me write this up. So we have this function, the inverse tangent or arctangent of 8 times the cube root of x. Now that's going to be equal to some series for the following values. When this value here is between negative 1 and 1, inclusive. Dividing by 8. Raising everything to the third power. Now 8 to the third power It's 512, all right? So this would be negative 1 5/12 and positive 1 over 5/12, right? 12. So, and then again, zeros in the center here. The distance to either end is 1 over 5/12, right? 1/512th. That's the radius of convergence for the series that would represent this function, the Maclaurin series. So 1 over 5/12. Great. Okay, here's find the first four non-zero terms of the Maclaurin series again. And they're giving you a little hint. Remember that cosine squared of something was 1 plus the double angle formula for cosine, 1 plus cosine of twice that angle, twice the input divided by 2. All right, so I'll write that up as a reminder. So it's been a while since we've seen that. Back when we were integrating trig functions, in the chapter 3 videos. So our function is 6 times cosine squared of 4x, which would be 6 times, and then cosine squared of 4x would be 1 plus the cosine of double that, right? Then all divided by 2. And then 2 goes into 6 3 times. All right, and then this ends up being just 3 plus, 3 times the cosine of 8x. Now I know the Maclaurin series for cosine of x, just cosine of x. Again, that's in this table. If you want to develop it yourself, you can. So that's it's cosine of x line here. So it's just alternating even powers over even factorials. So again, I'll write this up. Right, off to the side, the Maclaurin series for cosine of something, right? The cosine of x is this sum. Sum from n equals 0 to infinity of negative 1 to the nth times x to the 2n, so even powers of x divided by those even numbers factorial. And this converges for all real numbers, just like the sine and hyperbolic sine and e to the x and cosine, right? Oh, we're seeing cosine right now. And I'm just replacing x with 8x here. Right? 8x is replacing x. So when I write this as a series, this would be 3 plus 3 times the sum n equals 0 to infinity of negative 1 to the nth times 8x to the 2n over 2n factorial, and this should converge for all x still. All right. Okay, well, the first term is 3, and we might add on another constant. Let's see. No. 3 plus, and then 3 times, and I'm going to distribute the 3 after I write out the first several terms of this series. Now, they want the first 4 non-zero terms. I've already got one of them. Actually, when I put it, the first term in here is going to be a constant, so that'll make 1. So I will write out the first 4 terms in here. When n equals 0, you'd have, to the 0 power, to the 0 power, 0 factorial. That's just 1. When n equals 1, you got, minus 8x to the second over 2 factorial, then plus 8x to the fourth over 4 factorial. 2 factorial is 2, and then minus 8x to the sixth over 6 factorial, and so on, right? There's more to it, infinitely many more. But I'm just sticking with these 4 here, and then distribute the 3. Right. Now 3 plus 3, the first term is going to be 6. All right, 3 plus and then 3. First term 6. We have minus 3 times 8 squared over 2 times x squared plus 3 times 8 to the 4th over 4 factorial times x to the 4th minus 3 times 8 to the 6th over 6 factorial x to the 6th. And there's the first 4 non-zero terms of our series. And really, I'm just going to type it this way. So 6 minus 3 times, well, 3 times 64, 8 squared 64, divided by 2, x squared, plus 3 times 8 to the 4th power divided by 4 factorial, x to the 4th, and then finally minus 3 times 8 to the 6th power divided by 6 factorial, which is 720 times x to the 6th, and that should be good. I hope it takes it that way. Yeah, great. Now they actually multiplied things out and simplified. You got 96, 512, 16,384 over 15. But those are the same equivalent to my values there. All right, so yes, so now you've seen me complete that objective, and now I've done a video on all of them. All right, so I'm done with this video. So if you go look at my page, look back at you can see the videos for Taylor-Maclaurin series, Taylor's theory with remainder, binomial series, and now this functions expressed as Taylor series. Now I know they said Taylor series here, even though I think every single problem said Maclaurin series, but remember Maclaurin series is just a Taylor series centered at 0. All right, so that's it for this. As I said at the top of the video, right, just remember that the questions I saw here may not be exactly the same as the questions you see when you work on the assignment yourself, but I'm hoping that the problems are similar enough and the way I did them will help you when you work on them on your own. All right, thank you very much for watching.